This is section 7.4, which is systems of inequalities in two variables. We're going to talk about graphing inequalities, systems of inequalities, and linear programming. So the first thing, our steps for drawing the graph of an inequality with two variables is we're going to use, if we have the symbols less than or greater than, then we would use a dashed line or a dotted line. And then if you have less than or equal to or greater than or equal to, you're going to use a solid line. Then if you read the inequality out loud and you're saying y is less than, you're going to shade below. Or if y is greater than, you're going to shade above. You can always pick a point in either region and plug it in to see if it makes a true statement. And then you would know if it's true, you're going to shade that region. If it's not true, you would shade the opposite region. So our first example, we're going to graph y is less than or equal to 2x plus 4 and state the boundary of the region. So I'm going to go up to 4, and then my slope is up 2 over 1. So because this is less than or equal to, I know I'm going to connect those dots with a solid line. And then if I turn this to a highlighter here, so I'm going to shade below, because if I read that out loud, it's y is less than or equal to 2x plus 4. So I'm going to shade below my graph. I wonder if that's better. Oh, that's better. I should have done that. Let's try that instead. The paintbrush, much better. Okay, there we go. Okay, so that whole region is our shaded region. You can also pick a point, like if I plug 0, 0 in, it would be 0 is less than or equal to 4, and that's true. So you can notice that 0, 0 is shaded. Okay, so then the other thing is it says to state the boundary of the region. So we would say that everything on or below the line y equals 2x plus 4 is a solution to this inequality. Okay, so the next example is solving a system of inequalities graphically. So if we have y equals 2x plus 3y is less than 4, you can use the cover-up method where you say, okay, if I cover up the y, then I have 2x equals 4, so x equals 2. So that means my y-intercept is at 2. If I cover up the x and solve for y, I get y equals 4/3. Or 1 1/3. You could also solve that for y. So you could subtract the 2x, divide by 3, and get it into a slope-intercept form. So either way, however you would choose to graph it. And then y equals x squared is just going to be my parabola. Both of these do not have the or equal to, so that means it's going to be a dashed line or a dotted line for both of them. And so for this one, if we plugged in 0, 0, 0 is less than 4, so that's a true statement, so we'd shade below the line. And y is greater than x squared, so we'd shade above the parabola. So you can see in this final picture here that the double shaded region is going to be that solution region right there. So any point that falls in that double shaded region is the solution. Points that fall along the dotted line that is the perimeter of that shape are not solutions, because points on dotted or dashed lines are not solutions, only points on solid lines that border the region. Okay, so the last part of this is linear programming. So it says sometimes decision making in management science requires that we find a minimum or a maximum of a linear function. So what we're going to use is we're going to have what's called an objective function, and then with our linear programming, basically a linear programming problem is just like the previous problem that we did, where we have a system of inequalities that we're going to graph, and we're going to have a feasible region, so a double shaded or triple shaded region that we're looking at, that are created by constraints. So those are the inequalities that help us create the feasible region. And then we have vertex points or corner points. So those are going to be the specific points on the edge of our feasible region. So our last example here is to find the maximum and minimum value of the objective function f equals 3x plus 4y subject to the constraints given by the system of inequalities. So you can graph, you could type this into Desmos, you could find out the values. You can also graph by hand. But how we solve linear programming is you can see that this area right in here, let me use a different color. Go back to my paintbrush that I figured out 2/3 of the way through the year. Okay, so there's my feasible region. So I have 4 different corner points that I would find here. So this point right here is at the point 4, 0. That right there is at 0, 0. That point right there, you could find it graphically. You can also find it using the cover-up method. That's going to come from this equation right here. Is going to be 3.8. So it's going to be 0, 3.8. And then finally that corner point right there. So there's multiple ways you could find it. You could graph it. So you could graph it in Desmos, graph it on your graphing calculator, or you could take these 2 equations and find out the x and y. So set them equal, or use them as a system of equations. So find the x and y where they're equal. So you could do elimination and find that point where they are equivalent. And that point is 2, 3. So what we do with a linear programming problem is we're going to take that objective function and we're going to plug in all the points. So if I plug in 0, 0, I know it's just going to equal 0. If I plug in 0 for x and 3.8 for y, I get 15.2. If I plug in 2 for x and 3 for y, I'm going to get 18. And if I plug in 4 for x and 0 for y, I'm going to get 12. So this says to find the maximum and minimum values. So our maximum value is this point right here, and our minimum value is 0, 0. So we would say that the point 2, 3 maximizes these constraints and this objective function, and the point 0, 0 minimizes it. So depending on what you're looking for, that would help you with kind of a real-world context type problem. Okay, let me know if you have any questions about graphing inequalities or linear